All right, so we're going to continue with a bit of a review of stuff that you've seen most of this stuff from in pre-calc, although we'll be introducing some of the limit ideas and actually some derivative stuff here, but some of this is going to be review, but we'll be looking at inverse functions and in particular logarithms. First off, the definition of a one-to-one function. So some function f of x, we call it one-to-one if it satisfies this property that for any two different inputs, you're always going to get different outputs. So for any two different x1 and x2, the function value with those two is going to be different. So a one-to-one function passes a horizontal line test. There's nowhere on the graph of the function where you can put a horizontal line where there you have two x values that give you the same y value. That never happens on a one-to-one function. Okay, so a function is one-to-one if it passes a horizontal line test, which is to say there's no horizontal line that you could draw that's going to intersect the graph in more than one place. For example, if you look at the function f of x equals x to the third, the graph looks like this, and roughly, but you can see like no matter where you draw horizontal line, it's just going to intersect the graph in one spot. Whereas if you looked at f of x is x squared, the graph is you know parabolas, right? So it's going to look like this, and so it intersects it in two spots. So the first one, this is one to one, so x to the third is one to one, and x squared is not one to one. Okay. Now, if a function is one to one and its domain is a and the range is b, it's just two sets of real numbers. The inverse function is going to be denoted as f with a little -1 in the exponent, but it's not an exponent. We just put a -1 there to indicate that it's an inverse function. So just be clear on that. It's going to have a domain of b and a range of a, and it's going to be defined in such a way that the inverse of y is x means that f of x is equal to y. So it's a way of just undoing whatever the function f does to a value x. If you put x into the function, you get the value y. Put y into the inverse function, you're going to get the value x out of it. Okay, so say we have a very simple function that says, well, I don't know how this is as simple as a function can be. Is it's defined specifically for values. So like f of 1 is 5, f of 3 is 7, and f of 8 is -10. So we only have three values. So let's say this is the domain. I'll take the set A and the set B, and we have the values 1, 3, and 8, and the outputs of 5, 7, and -10. So it says that f maps the value 1 to the number 5, the number 3 to the number 7, and 8 to the number 10. So because there's no two inputs that give you the same output for this function, we can define the inverse function, which is going to say, well, the inverse of 5 is going to be 1, the inverse of 7 is going to be 3, and the inverse of 10 is going to be 8. That's how you define the inverse. You just go backwards. As long as no two arrows map to the same number, you can do that. Okay, so now if we take the inverse of the function for any value x, the inverse f inverse of f of x will just give you x again. And that would be true for all x in the domain, and f of the f inverse of y is going to give you y for any y in the range of f. So it's kind of, you go back on the arrow and then forward on the arrow, or forward on the arrow and then back on the arrow. Okay, so to find an inverse function algebraically, if you have a function f, here's what you want to do. First you want to write out y equals f of x. All right, next we want to solve the equation for x, meaning x equals some stuff, where the stuff is only in terms of y, if possible. If it's not possible, then, well, you can't do it. It doesn't mean it's not one-to-one, it just means that it might not be something that's really doable with the skills you have. or it may not, they may not have some closed form or something like that. But anyway, you do it if possible. Okay, so then you interchange your x and your y's, and the resulting equation will be your inverse function, y equals f inverse of x. For example, let's take f of x equals x to the third plus 2. So the first step was to write y equals x to the third plus 2. And now I'm going to solve it for x. So first thing, I'm going to subtract 2 from both sides, right? And then I'm going to take a cubed root of both sides. The cubed root of y minus 2 equals x. And so I'm going to then replace the y, swap the y's and the x's. Y equals the cubed root of x minus 2. And so f inverse of x is going to be the cubed root of x minus 2. So this swapping of the x and the y's can be thought of in terms of, like, graphically. The graph of the inverse function can be found by just taking the graph of f and reflecting it over the diagonal y equals x. Let's take a look at the example. Okay, so let's just try to do this graphically. So the graph I'm looking at is the graph of f of x equals -1 minus x. So remember, so we want to think about how you would graph this. Let's see, that's probably the simplest way to think about this is we know that because we have negative x in there, this has been reflected horizontally. And now just think about what f of what is going to give me 0. And that's going to be when x is at -1. F of -1 is going to give me 0, right? So I'm going to, the graph is going to look like this. F of -1 is going to be 0, and so this thing is going to go up like this. It's going to hit these marks. Okay, this is y equals f of x, and so the diagonal of reflection is going to be this diagonal here. And so what I'm going to do is I'm going to take this graph, reflect it over, it's going to look roughly like that. Put a little dot there. Oops, put it in red. I wanted to put it in black. Okay, so this is going to be y equals f inverse of x. Okay, so that's the idea for reflecting over this diagonal. Okay, this is a theorem, a fact about continuity. If a function is one-to-one and it's continuous, its inverse is going to be continuous. Okay, which makes sense because visually, how could you get discontinuities if all you're doing is reflecting it, right? Any continuity you have is going to be preserved in the reflection. Okay, now a theorem about differentiability of an inverse function. So if you have a function f that's one-to-one and differentiable, and then you have its inverse is f inverse, right? F to the -1. Now, as long as the derivative, so now we're interested in the derivative of the inverse function at a, where a is in the range of f, right? So as long as the derivative at, let's say like with the value that in function, the value of f, the value in the domain of f that gives you a, right? Call it like, I don't know, b or something, where if f of b is equal to a, f inverse of a would be b. As long as the function f doesn't have a zero derivative there, then f inverses would be differentiable at a, and its derivative would be the inverse of the derivative of f at f inverse of a. Let's take a look at an example. Okay, so my function f of x is 2x plus cosine x, and I'm interested in finding the derivative of the inverse function at 1. So what I need to look at is what value of x is going to give me 1? 2x plus cosine x equals 1. So you can solve this actually, and you're going to get x equals 0, right? Because the cosine of 0 is 1. 2 times 0 is 0, so you get 0. Now, what we do is we find what is the so this 0 we found, this is the f inverse of 1, right? That's what we were trying to find. And so let's find the derivative of our function, f prime of x. That's going to be 2 minus the sine of x. So let's find the f inverse at 0. That's going to be 2 minus 0. That's going to be 2. So this theorem tells us that the derivative of the inverse at the value 1 is going to be 1 over the derivative of our original function at the value that gave us 1, which is going to be the derivative when x is 0, which is 2, so 1 over 2. Okay. Now what this is really saying is that this is like the slope of the tangent lines. When you reflect over the line x equals y, the slopes are going to be reciprocals of each other at corresponding points. That's what this is really getting at. Okay, so now we're going to speak specifically about logarithmic functions, which in the previous video I looked at the exponential function. Well, the logarithmic function is the inverse function for an exponential function. Specifically, okay, so the logarithmic function with base a is denoted log with a little a in the subscript there, such that log base a of x equals y is equivalent to a to the y equals x. Okay, so a little theorem, which is just applying what we talked about with inverse functions. Because they're inverse functions of each other, the logarithm base a of a to the x is just x. And a to the power log base ax is equal to x. Because you've got to remember what a logarithm is saying is log base a of x equals y. When we say that, we're saying the exponent that turns an a into an x is y. So if I say, what's the logarithm base a of a to the x? I'm asking, what exponent turns a into a to the x? Well, obviously, it's just x. Then on the other side of things, a to the power log base ax is, remember, log base ax that's the exponent that turns a into x. A to that power gives me x. Well, if you take a and raise it to that power, then you're going to get x. That's what it says. Okay, so now some laws of logarithms. As long as x and y are positive, here are some properties of logarithms. First off, the logarithm base a of a product x times y can be split into the sum of two logarithms, log base a of x plus the log base a of y. Secondly, the logarithm of a quotient is going to be a difference of two logarithms. So log base a of x over y is log ax minus log ay. And thirdly, the logarithm base a of the power x to the power r will be r times log base a of x. And so you can think of it like, what exponent is going to turn an x into x to the r? If you raise it to the log base a of x, that will turn a into the x, and if you then raise that to the power r, it's going to become x to the power r. Okay, so now if you for example, if you have this logarithm, you want to try to try to simplify it. What thing you can do is realize, oh, this is a difference of two logarithms. So that's actually the log base 2 of 80 divided by 5, which you guessed it is going to be log base 2 of 16. And now you can actually ask yourself, 2 to what power is equal to 16? And that answer is 4, right? So log base 2 of 16 is 4. So the limits of a logarithmic function, as long as the base is greater than 1, then the limit of log base a of x as x goes to infinity is infinity. And the limit as x goes to 0 from the right is going to be negative infinity. And the reason is that the logarithmic functions really are going to look like this. This is what log y equals log base a of x looks like. This is the flip of the function a to the x, right? And so you think it's over the diagonal y equals x. Okay, so as an example then, let's look at this weird logarithm. The limit as x goes to 0 of log 10 of tan squared x. Now one thing to remember is that tan squared x is going to always be greater than or equal to 0 because it's tangent squared, right? So as x goes to 0, tangent squared x is going to approach 0 from the right. And so we can let's call this t. And so this logarithm is the same as the limit as t approaches 0 from the right of log base 10 of t. Now I didn't actually, you could plug in 0 for the tangent squared of x and you'll get 0. So I didn't say that, but yeah, that the tangent just is continuous at 0. So the limit is 0. But the point is that tangent squared is going to be approaching 0 from the right. Whether x is going to 0 from the left or the right, the tangent squared x is only approaching from the right. And that's important because then you can say, oh, this is going to be equal to negative infinity. Doesn't matter what the base is. Base is 10, base could be 100, base could be 5 million, doesn't matter. It's still going to approach negative infinity. Okay, so now the natural logarithm. It's a very important logarithm. As you probably guess, e is involved because we talked about the natural exponential function. Okay, so the natural logarithm is the logarithm with base e. And so instead of saying log base e of x, we'll just say ln of x. And I think ln stands for log natural, and it's French because the French mathematicians spent a lot of time with logarithms and stuff. In fact, Euler, who the E is named after, he was Swiss, and if he was doing French math, then he probably named it ln for that reason. And note, just to continue with the definition of the natural log as far as a logarithm goes, if you have the natural log of x equals y, this is equivalent to saying e to the y is equal to x. Okay, so a little mini theorem that pops out of this is just the definition, or this is just a special case of a theorem that we looked at a bit ago. The natural log of e to the x is going to be x, and the e to the natural log of x power is also going to be x. And this is just a special case of a theorem we looked at a couple of slides ago. Okay, so if you wanted to actually solve the natural log of x equals 5, well, what we can do is we can, knowing that e to the ln x equals x, we can actually say, well, if these two things are equal to each other, then e to the ln of x is going to be e to the 5. If two values are equal to each other, then e to that one power is equal to e to the other power. But the left-hand side just becomes x by this property. So x is going to be e to the 5th. Okay, as another little example, let's take e to the 5 minus 3x and try, equals 10 and solve it for x. So similarly, we can use the property that the natural log of e to some power will essentially cancel it out. So the natural log of e to the 5 minus 3x must equal the natural log of 10. On the left-hand side, this becomes 5 minus 3x. And so now we can solve for x. We can, let's subtract the natural log of 10 from the left-hand side, and let's add 3x to both sides. I just like to have the positive x, so I don't have to deal with dividing by negative numbers. Now I'll just divide both sides by 3. And so, we can say 5/3 minus the natural log of 10 over 3 is equal to x. And so that's the idea. Let's take another little example. Let's look at the natural log of a plus 1/2 the natural log of b. And I wanted to just look at how you would express this as a single logarithm. So the thing to do is to first we've got in order to add two logarithms together, you can't have coefficients. So the natural log of a is fine, but I'm going to write this as b to the 1. Oh, sorry, it's the natural log of b to the 1/2 power, which actually I'm going to write as the square root of b. And then the sum of two logarithms is the natural log of the product, a root b. And there you go. This is a way of combining a sum of two logs, this expression. Coefficients can go as the exponent of the thing inside the logarithm, and then you can multiply the a and the root b. So here's a special formula that's useful, especially if you don't happen to have a fancy calculator, I guess. But I don't know. For any positive number base that's not 1, because a logarithm base 1 doesn't really make sense to talk about, because 1 doesn't matter what power you raise 1 to, you'll never get anything besides 1. But the logarithm base a of x can always be written as a natural log of x divided by the natural log of a, whatever that value a may be. So for example, if you wanted to evaluate log base 8, 5, and you don't happen to have the ability on your calculator to do a logarithm base 8, what you can do is just take the natural log of 5 and divide it by the natural log of 8, because you probably have a natural log button on your calculator. Okay, so now I want to just do another example where I'm actually I want to graph out the graph y equals the natural log of x minus 2 minus 1, and I think it's going to be helpful to just think about this in terms of asymptotes. So I'm going to draw some axes we can use for this. So if you know that the natural log, this natural log, as the lowest it can get is it can go down to negative infinity, right? And it can go up to positive infinity. The x minus 2, that thing inside, has to be strictly greater than 0, which means x is going to be greater than 2. So at 2, we actually end up with an asymptote. So if we were to plug in for x equals 2 and plug that in, remember one thing that's important to know is like the natural log of 1 is going to be 0. So that's an important point. So when x minus 2 equals 1, that means x is equal to 3, right? So when we are at 3, then if you plug 3 in, you're going to get 0 minus 1. That's going to be this point here. That's the point 3 comma negative 1. That's like the one anchor point. Once you have an asymptote and the kind of this anchor point, then you can sketch out the curve. And just as long as you have the asymptote go in the right place, and then you kind of have it go like this, that's good enough. For the natural log function, it should look like that. So you have your asymptote, your anchor point, and then you can sketch the curve and just have it getting bigger in the right direction. So this was our kind of a crash course in inverse functions and natural logs or logarithms. Hopefully this is kind of coming back, and you can see how these ideas about continuity and limits relate to these natural logarithms and so forth. That's it for now. Next video, we're going to now look at derivatives for exponential and logarithmic functions.